Giuseppe. I'm a member of the Logic, Uncertainty in Computation and Information Group at the University of Milan, the Department of Philosophy. And this is joint work with Fabio, which you have actually met last week, I think, or 2 weeks ago. Well, it is the first work that we hope it will come out under this new research project that we have ongoing, which is focusing on bias, risk, and opacity in AI. The title of the talk is Checking Trustworthiness of Probabilistic Computation in a Typed Natural Deduction System, and I hope I'll hope to give you an idea of what the system is, so do feel free to interrupt me if you need any clarification. So I do prefer that then rather than losing you midway. So let me start with a little bit of an overview of the talk. I will give you an example. This example is obviously a little bit far-fetched, but maybe not so much. Hopefully, though, the example will tell you a little bit about what type of problem we are looking at. And then I will move into the formal aspect of the work, namely introducing this calculus, which is called TPTND, which stands for Trustworthy Probabilistic Type Natural Deduction Calculus. We will go back to the example in order to see how the formalism applies to the case we are looking at, and then I will mention a few meta-theoretical results. Those results will obviously be theorems for which I will not give you the proof here, but again, I hope to give you a flavor of what the meaning of those theorems is. And then I'll mention some related work that we are doing, which is close to the present one. All right, so setting the scene. Imagine you have this logic group in some university, which we call the University of Uncertain Land, and they are advertising for a tenure-track position. There is a huge number of applicants, and so the dean tells the selection committee, we actually have a machine learning program that we have purchased, so that you can use it. And what it will do, it will basically shortlist the candidate based on some criteria that are well defined. Okay, so what are these criteria? And here we have obviously to assume that this, let's assume for the sake of the argument that it is not problematic to have this criteria checked in an automatic fashion, right? So I'm not saying that this should be the case, but just making the case for my calculus. So the admissibility criteria for the candidates on which basis they will be shortlisted is that they have to have either a PhD in computer science or in philosophy. They have to have at least 3 years of postdoctoral experience, and the gender does not matter. So far, so good. I mean, these are properties that we can actually let a machine check. The fourth one is maybe a little bit less, a little bit more risky, if you want, in that we want, of course, to rank them on the basis on some quality of publication and quantity of publication, right? So, but let's assume that there is an algorithm that does that ranking, and that is not problematic. So this will generate some ranking, and it will shortlist certain candidates. Right, so what is the type of problem that we want to look at this point? We want to ask ourselves the following question. Which shortlist distribution given as an output by our algorithm should be considered fair with respect to the distribution of some given property in the population of interest? For example, gender. Right, we want to ask, is the shortlist that we have fair with respect to how many, say, female or non-binary people identify in the population that is allowed to apply? And second step, can it be verified automatically if the program is trustworthy with respect to the distribution? In other words, can we check that automatically that the program does in fact produce an output which is sensible to the distribution, say, of female candidates in the population of interest that is applied, so that the output generated by the machine is in some sense close or fair with respect to the distribution, right? So this is our problem. We are rephrasing slightly the issue of trustworthiness in terms of a fairness criteria. Notice, and there are people, I think, attending. I know, I don't think so. There are people attending this talk that have a very clear idea of the huge amount of work done in computational trust. I'm not saying that this is the definition of computational trust. I think many would agree that there are enough different definitions for this to be one such. All right, so what is our approach to the problem? Well, we develop a natural deduction system, which is designed to reason about probabilistic processes with respect to two properties of interest. The first is a property of expressed in the theory. The second one is a property which we analyze at a meta-theoretical level. So the property expressed in the theory is trustworthiness, and it is defined as a measure of how close the frequency of a probabilistic output gets to an ideal distribution. Notice that this distance should be parametric with respect to the number of executions of the process. In other words, one expects that a trustworthy program, the more it is executed, the closer its output gets to the ideal distribution of the input. The second, as I mentioned, is a meta-theoretical property. It's what we call safety. The name is actually the name that is typically used in this type of calculus for a meta-theoretical property. And in the interpretation that we give in the present context, it serves the purposes of guaranteeing that there are no unintended results allowed by any execution of the process beyond a reasonable probability. And this is, so explaining more in detail what the safety property is will be the task of the last part of this talk, where I will go into some meta-theoretical observations or comments. All right, so what is the structure that we develop the calculus with? So I've listed here 6 points, which I hope will help in going through the formal aspects of the language. So first of all, what we do is we provide an inductive construction of probability distribution. So we want to describe the input given to the program according to some probability assigned to the distribution, to the data points in the input. Second, we provide a set of rules that allows us to reason about variables in such distribution. So you will have a first fragment of the language which makes inferential reasonings about random variables only. A second fragment of the language will allow us to reason about processes. And these are deterministic processes first. So these are essentially execution of a program which gives a deterministic output. And then we generalize this to multiple execution, in which each individual execution is deterministic, but the overall output of n number of execution will have associated expected probabilities on the outputs. And then we will be able to reason about expected probabilities under random variables. In this second fragment, frequencies are individual instances of such processes. So it's the counterpart of the empirical probability of this execution. There are then two sets of rules, which are respectively structural rules for the calculus, which allows us to reason about deterministic and non-deterministic processes on distributions. And the final set of rules is the rules for establishing trust on processes, in the sense that I have explained it, namely checking that the frequency of a given output is close enough to the expected probability, so to say. Okay, so basically the rest of the talk will be translating these 6 points into their formal counterparts, if you want. Okay, let me start with the syntax. The syntax of the language TPTND is built out of variables X. So the set X here is a set of variables, for random variables, and they are structured for doing operations, so connectives, if you want, on them. So we have simple random variables. We have random variables which have an associated process, T. So this will be useful for when we want to say that a given process is an output depending on the corresponding probability of that output. We will be able to build pairs of variables, extract the first and the second projection on those pairs, do abstraction, do composition, and this composition can be done both with respect to variables and with respect to terms. Notice that this is not entirely standard. In usually what you will expect here in, say, a lambda calculus is that you have an abstraction of a term with respect to a variable and the composition of a term with another term. But here, remember that our calculus is divided in two fragments. In one fragment, we are able to deal only with variables. In the other fragment, we are able to deal with variables and terms. So for this reason, you have here abstractions of variables and applications of variables, while the application of a variable to a term will be useful to express by using updating. So once I introduce the rule, hopefully all of this will become evident. So we have variables, we have terms. This is the set T. So we have simple terms, we have pairs, we have the first projection on a set of a pair of terms and the second projection. We have an abstraction. So this is the standard construction of a lambda abstraction, and this is the standard application of a lambda abstraction. And then we have two function-like operators. They are listed as connectives, in fact, but the reason for that is because they behave as other connectives in that they have both an introduction and an elimination rule in the semantic. But in fact, they look more like a function, and these are a function to trust a term or a process, if you want, and a function to untrust. So this is the expression for negative trust. The set O is the set of our types, which we look at as outputs. I will give in a second an example of all these expressions so that this will become clear, but outputs are simple, so atomic types, with a probability value attached to them. So R is a meta variables in the set of reals. We use bottom when we have to denote no output or non-termination, if you think in terms of computational processes. We have times for conjunction and plus for disjunction, and we have an implication. And notice that all of these are indexed with appropriate probability values. C is our set of context, where contexts are our probability distribution under which we make inferences. And basically, we will start with an empty context, and we will build up the context inductively by adding judgment that says that variable X is assigned output alpha, and the judgment that says that variable X has a probability A of having assigned output alpha. S are statements or type declaration, otherwise known as type declaration. So simply the declaration that alpha is an output and are in the set of reals, and these are typically preconditions for the other judgments to occur. So let me give you an example of what type of judgments do we look at in our language. The following judgment says that the random variable epsilon has a probability 0.1 of producing output beta, provided variable X as output alpha. Okay, so this is an inference made about relations between random variables, dependency relation between random variables, where the, so to say, the antecedent or the condition is deterministic, and the conditioned or the consequent, if you want, is probabilistic. We will see that, in fact, we can attach a probability also on the condition. Right? Right, so a second type of judgment that we can express is when we look at terms in the right-hand side of the derivability relation. So this judgment says that under distribution gamma, where gamma will be a set of formula of the form x in alpha, for example, gamma could express the probability distribution attached to a slightly unfair coin. So we will have a variable x that has two possible outputs, then heads and tails. And if the coin is slightly unfair, for example, heads might have a slightly lower probability than 0.50 to come out, say 0.35, 0.35. And then what we can derive is the claim that tossing the coin 100 times, we expect the probability, we expect to get heads 35% of the time. So notice that here we use a notational device, namely the tilde, to denote that this is an expected probability. Obviously, the expected probability that has the maximal probability to occur is exactly the probability assigned to the variable heads in the corresponding distribution. So if our coin is slightly unfair in terms of having heads occurring, say, 35% of the time, and tails occurring 65% of the times, then on 100 toss, the expected probability of getting heads will be exactly 35%. So these are two different types of judgment, both occurring in our language. There is a third type of judgment occurring in our language, namely the frequency of the result of a given, say, a set of tosses. Namely that over 100 tosses of our coin, the output heads was obtained 30 times. Now here, this is no longer an expected probability, but is literally a frequency, right? So notice, of course, that while this value matches by probability laws, matches the corresponding value of the corresponding variable in the input distribution, this value does not need to. And the point of the trustworthiness operator that we are going to define is exactly that of checking whether a value like this is close enough to the value that is expected. Okay, I hope this anticipates a little bit what the trust operator does in our case. The point is that in order to get there, we need to have a sufficiently expressive language to account for all these different type of judgments.
Excuse me, Giuseppe. Mirko
Yes.
has a question for you.
Mirko, yes, please, Mirko.
Yeah, so just a really quick one. So the subscripts, do they have different meanings, or is just like a typographical way of representing a process? Because 100 sometimes is number of tosses, sometimes it's just the probability of an event.
No, so okay. So thanks for that. So subscript on terms, like if you want the left-hand side element of a column, is always a natural number. It always indicates a number, the number an events has occurred or will occur.
Okay.
While subscripts on types are always probabilities, either, or I should say, either probabilities or frequencies in this case.
Okay. Okay. Thank you.
Yeah. Thanks. All right. So we start with. So let me, for those maybe not acquainted with this type of calculus, recall that I'll say that rather than recall, because you might not know. The idea of a typed natural deduction system is that first your judgments are typed in the sense of having a structure of this form, where this is, in our case, the output of a variable or the value of a variable or the output of a process. So typed in this sense. Second is that connectives are all defined by introduction and elimination rules, right? So all the semantics of the language is generated by providing proof theoretical operations that tells you what to do with your expressions. The first set of rules tells you how to construct the object on the left-hand side of your judgment. Remember that these are intended to express distribution on the input of interest. So the construction is inductive. So we always start with an empty distribution, and then we can extend the distribution with two types of judgments. The first is the assertion that a given variable has an output alpha with a given probability A. In this case, what we want is that we can add that judgment to a given distribution only on condition of just let me say, this is the additivity condition typical of probability theory, right? So all the output possible for a given variable x should so all the probability on the possible output of a given variable x should add up to 1, right? So because that's how probability works, right? All the outputs, say if you think of a coin, you will have here heads and tails as possible outputs, and whatever number you have here, their sum should be 1, because these are the only two outputs. So this third condition here is your additivity condition. But you can also extend a distribution with a deterministic process, namely a process that has no probability attached to the output, but it simply generates that output. This is the case of x in alpha. We have one specific type of output which is interesting for our case study, namely the unknown distribution. You know nothing about what you have in your hands. You don't know nothing about what type of coin they've given to you to be tossed. So what you do is you assume that every possible distribution is admissible, right? So you, in this case, if your output are heads and tails, what you will say is that your distribution assigns any value to heads in the range 0, 1, and any value to tails in the range 0, 1, preserving the additivity condition. This is why is the unknown construction of a context interest is useful, because what we specific case we want to consider is when the program that we are running is the typical or prototypical black box, right? We don't know how it works. We can only observe its behavior. And then in that case, what we are considering is a case where we do not know what probability does the program assigns to its possible input. All right, so distribution formation rules. So the next step, for example, the theoretical probability distribution associated with the outputs of a fair die D is the following: is a set of 6 judgments, or 6 type declaration, more precisely, in which a variable x is associated to the die D, and each of output is the output 1 to 6, where the probability associated to each output is 1/6. So the description of the probability distribution of a fair die will be something like this in our language. Or if you are looking at 2 coins, which are one is fair and the other is biased, you will have a probability distribution which looks like this. You have 2 random variables. They are independent, namely x and y. They are associated to 2 different, here I'm using D, I should have said C for coin, but say D and D prime are the 2 coins that are not dependent on each other, right? So they are 2 independent systems. And the first coin, D, is fair in that the probability associated to heads and tails is 1/2. but the coin D prime is biased in that the probability associated with heads and tails, typo here, sorry, are respectively 1/3 and 2/3. Okay, so this is the type of set of expressions on the left-hand side of our derivability sign. Okay, so now what we can do is make inferences on the very same variable. We have two identity rules, respectively, for deterministic and probabilistic random variable evaluation. So identity one says that given the probability, given the variable x is assigned value output alpha, the probability that x has output alpha is 1. And the generalization of that is that given that variable x has a probability a of having assigned output alpha, then the probability that x has output alpha is a. Right? These are simply the two variants of the a implies a axiom for our logic in respectively the deterministic case and the probabilistic case. By the additivity condition on distribution construction, we get our dual of the probability, namely if under gamma we can derive that variable x as a probability a of having assigned output alpha, then the probability that x doesn't have output alpha is 1 minus a. And then we can construct our connectives. So we have times for the conjunction of independent variables. So here you have under distribution gamma, x as probability a of being alpha, and under distribution delta, variable y as a probability b of having beta assigned, and gamma and delta are disjoint, so they are independent variable set. Then you can construct a pair xy where the output a and alpha and beta has probability a times b. You can eliminate the conjunction by projection on the first projection, respectively second projection on this pair. Remember that this object here, x, in order to have this type, alpha times beta, must be a pair. So we can do the first projection on x. If we are able to extract the probability a of alpha, then we can determine the probability c over a of beta, and so for its dual, namely the second projection, which gets the probability of the first. For times, this is the disjunction of two possible output of the same variable. So if the variable x has a probability a of having output alpha and has probability b of having output beta, then x will have alpha or beta with probability a plus b, which is again the additivity conditioning at work. And in fact, you see here the elimination of plus by getting say the dual of any of those output. In other words, if I know that x can give me output alpha or output beta with probability a, and I know that x does not give me alpha with probability a prime, then I can infer the probability that x gives me output beta, and so for the other output. And then we have here the construction for the implication, which typically in this type of calculus, you have to see implication introduction as modus, as deduction theorem, and implication elimination as modus ponens. That's where the inferential engine of the implication is at work. In our case, the implication introduction is nothing else than a rewriting of dependency for variables. So here we say that y as probability b of getting output b, of having assigned output beta, provided x as output alpha. I can rewrite this judgment as an implication. Now we'll have, so you see here, which is a little bit unusual way of writing for who is acquainted with lambda calculus, is typically you will have here x, you will have a term, and this will be the abstraction of a term with respect to a variable, while here we are working just with variables. So the type of this object here will be alpha implies beta with probability b. How do we eliminate this object? Well, we have to get x to have an output alpha, and that could be with any probability a, right? Then the probability that y has output beta, given that x is alpha, will be resulting by a times b. Notice obviously that if this is a deterministic judgment, namely I execute, I have a variable x, and the only value that I can assign to x is alpha, then the all probability is at work is that of beta, so the probability b remains, and that will be 1. All right. Okay, so this is the fragment of the language that allows inferences over the dependency of the random variables in the distribution. The next, so here an example. So say that we want to model a distribution where we have two random variables corresponding to 2 coins, and we know that the first coin x is fair. Now, what we know is maybe a strange system, but we know that whenever x returns tails, y will return heads, and the other way around. There's some strange mechanism at play here, but they told us this is the case. So we can express that in our language by writing this type of judgment, respectively, y as output tails with probability 1 whenever x is heads, which we can write like this, and y is heads with probability 1 every time that x is tail, whenever x is tails, which we can write like this. To verify that this is the case, well, what we need to do is eliminate this implication, which we do by verifying that x is indeed fair, namely that x gives heads 50% of the time. So we will need this assumption here, and then we'll know that y has tails 50% of the time, namely matching the behavior of x. This is a simple example of type of implication or dependency between variables. Okay, Pierluigi, please let me know when I am approaching, say, 10 minutes so that I can...
Yeah, you have 20 minutes again.
Okay, okay, thanks. All right, so now what we do is we look at the fragment of the language which allows us to deal with experiment executed under a given probability distribution. And here we use terms now on the right-hand side to denote this idea of a process or an experiment. And notice that now variables get associated to terms, right? So this is because we want to express that these terms depends from the value of this variable. Now, while this might be obvious in light of the fact that these two objects have the same type, obviously once objects have complex type, the type don't match anymore. So we need this sort of slight notation trick to make that connection relevant. So what does this axiom say? This is the form of an axiom, so it's a rule without premises. It says, well, process T as output alpha whenever x as, or provided x as variable, x as value alpha with probability A. And notice that here the experiment is deterministic, right? So you do the experiment, and if you do the experiment will give you one output. Now we can do the same type of rules that we have
Giuseppe,
used. Yes, Vincenzo, please.
It is enough that A is more than O.
Well, I suppose you mean the A on alpha.
Yes, yes.
Yes. Although
Here
notice
there
that
is,
notice that you might have cases where this type alpha and this type alpha are distinct, and then you might even have 0 in A here. But you might have a process that gives you a certain output if and only if another variable has no probability of getting another output. Right?
okay. The second alpha is not the same. Okay.
Doesn't need to be the same. This is
Okay.
the standard way of expressing it, but once you generalize, this doesn't need to be the case.
Okay, thank you.
Okay, so then we can do exactly the same work we have done with the other connectives, namely we can introduce and eliminate conjunction. So here I'll just say a few, just not to repeat all over myself. So process T as output alpha under distribution gamma, and process U as output beta under process, distribution delta, and assuming gamma and delta are disjoint, then the pair of processes TU gives output alpha and beta. You can eliminate the same way we did, this time by associating probabilities here, obviously, and you can do the disjunction with processes the same way we did with variables, and you can do the implication. So let me just read you this because this is now interesting. So this says, so you see here we have the case was mentioned before where those two types are not the same. So T as output beta provided X as probability A of getting alpha, of value alpha, which we can rewrite like this. And if this is the case, and we can execute a process U with output alpha, this is what we substitute for X here, and we get that T actually gets output beta provided U as output alpha. So here is all deterministic, right? So at this stage now, we have basically eliminated all the probabilities. When do probabilities come back in the form of expected probability is when we execute the process T more than once, right? So if I now do not limit myself to, say, toss the coin once, but I toss the coin 100 times, as I did in my initial example, then the probability of alpha will have the output alpha, will have an expected probability A. And this expected probability A will match for the maximum likelihood principle will match exactly A. So if the variable X for a process T has a probability A of getting output alpha, N execution of T will have expected probability A of getting alpha. Notice though that while this is basically trivial, right? So because once you know or you assign this probability, theoretical probability, this essentially has to match because otherwise you are not working with correct probabilities. A sampling on T does not necessarily need to, right? So if I now actually run T n times, right? Individual n times, right? And I look at the output, there is no reason why the frequency f of alpha has to match the expected probability. And that's, in fact, the problem that we want to or expose rather than address, expose in the calculus. Right, so what we are looking at now is the purely theoretical realm in which probability are assigned and then expected probability match to that, to the more empirical case where by running tossing my coin 100 times, I will most likely not get heads 50 times, right? So here F is now the notation that we use to express the frequency of alpha over n cases. And it is on that frequency that we can do update. Namely, I run T n times and I get alpha with a frequency F. And then I run Tm distinct time, and I get alpha with a frequency f prime. I can update that value over n plus m cases with the standard update equation that is usual to do. Okay, so here the crucial point I'm trying to point out is that at this point we are looking at literally two epistemologically different phenomena, right? On the one hand, theoretical probability and expected probabilities, on the other hand, frequencies. So example, now we are given a die and we know nothing about this die, right? In particular, we don't know whether this die is fair or not. The only thing we can say is that we can assign the unknown probability distribution to the die. So gamma here expresses that by saying that every output 1 to 6 has some probability between 0 and 1, and we don't know which, but their sum will be 1. Now, what we can do is we run die 1, the die we have given, 4 times. And for example, we get these outputs, 1, 1, 5, and 6. And we can say, well, out of 4 times we throw our die, we get 1 half of the time. And then we do it again. Say we run D again another 4 times, and we'll get different outputs like 3, 1, 5, and 6. So 1 is now 1/4 of the time. And we can update in this way, all right? Over using these two trees, we can say that over 8, so 4 plus 4 throws of our die, we got output 1 3/8 of the times. And we can do this as much as we want. Obviously, the intuition that we know from probability theory is that the more this approximate to an infinite number of throws, the more this value should be 1/6. So in this case, it's a die. Another example, I can do the same type of update with first doing a or introduction. So I have the first die got me once 1/2 of the time. The second, in the second set of throws of the die, I got 3 1/4 of the time. So from the this should be this is actually the same throw, right? I got 1/2 of the time and 3 1/4 of the time. Then in the first 4 throws of the die, I got either 1 or 3 3/4 of the time. And I can do the converse of all of this. Another example is I can get pairs, so I can get all the possible combination of outputs and say that, for example, if I have two dies, one of which gave me the series 1 3 5 1, and the other one which gave me the series 2 3 6 1 4 4, then on 4 throw of the first die, I got 1/1/2 of the time. On 6 throws of the second die, I got 2 1/6 of the time. Then I got the pair of those 2 throw with the possible 24 combination got me 1 and 2 1/2 of the time, and I can eliminate. So this is just to tell you that I can do basic probability reasoning with my operators. Okay, I'll skip this because so another interesting thing that we can do is do Bayesian updating now. So these 2 rules introduce an operator to update our probabilities. How we do this? Well, assume that we have a series of judgments of the form y as probability B1 to get output beta, provided x as probability A1 to get alpha, up to those probability are different, right? So y will have probability B n of getting beta, provided x is probability alpha. So these are a series of hypotheses you do on the relationship between 2 variables. The probability of B1 to Bn should still amount to 1. Then you can derive a series of implications, right? So these are all the implications that you can construct from each of this judgment. Now what you want to do is to update this information that you have. And how do you update it? With some experiment that you are doing. So if you now throw your die or toss your coin or whatever you have in your hands n times, and you get alpha with a probability, with a certain frequency f, so this is the experiment that you are doing, you can use this information to update the probability of either of these. So you will select one of these and use the frequency here to update the premise and update the probability of the consequence. This is the definition. So this B here is this equation here. So you take the value of A on the frequency F. So this AI is this assumption here. And you multiply for all the times that you did not get that probability AI times the probability of the BI that you are considering on the output over the sum of all the possible cases, the probabilities of all the possible cases. So this is basically how to update the value of a variable based on the value of a certain experiment, of the frequency of a certain experiment. Okay, structural rules. We have two structural rules. Cut rule is admissible, but we don't need to go into that. What do weakening and contraction tell us? Well, if I have a variable z which has probability b of having output beta, provided x has output alpha, and y has probability g of getting output gamma under delta, and this assumption and this probability distribution are disjoint, are independent, then I can extend this judgment. I can extend this judgment with delta, right? So the usual meaning of weakening in standard proof theoretical setting is that I can add assumptions to judgment. Here is the same, I cannot add assumption to context. Here the idea is the same, but we need to enforce the condition that the a probability assumption that I add to my context is not relevant for the probability distribution that I'm already using. So it needs to be disjoint. Contraction, the usual meaning is if you have more than one assumption with the same value, you can just use one. In our case, our assumptions are with probability values. So what does this mean? It means I'm doing an experiment which has a series of possible assumptions on probabilities for those variables. Well, I can select one of those. Here we use a generic function because it can be whatever function you need. There is one obvious function that we want to use here as the maximum likelihood function, right? So if I want to determine which probability on alpha is the correct theoretical probability for beta with frequency f, well, I have just to select exactly the maximum, the probability value that maximizes the probability of t getting output beta with frequency f. This is just how the meaning of certain structural rules get into this language. Okay, let me get finally to the trust fragment, which is the one we are the most interested in. So remember the intuition. What is the intuition? Now I have a way to express theoretical probability distribution, and I have a way to look at experiments or execution of programs that have probabilistic outputs under distribution that are possibly unknown to me. So assume that this is the case, right? So you know that you have some distribution that is your ideal case, and you are now observing a number n of execution over process u, which give you frequency f for output alpha. Now your question is, can I trust that this output is admissible or is desirable under this assumption, under the assumption that there is a certain distribution which I think is the correct one? Well, we infer trustworthiness if the distance between those two values is below a certain threshold. Here, think of this as the confidence interval that you get by centering on this value and execution, right? So if this distance is, say, confidence interval typically gets 95% in the binomial. If you get inside that confidence interval, then you will say that this process is trustworthy. If it is not, you will say that it is not trustworthy. I want to give you the example so that this becomes hopefully immediately clear. So let's go back to our initial example. We have our program has selected a number of candidates, is checked yes, no conditions on the admissibility criteria that were listed by the committee, and it has generated a shortlist, okay? So what we get is that we get, say, 10 shortlisted candidates. Out of those, 3 are female, okay? So how do we say this? Well, we say it like this. We say there are 10 candidates and the probability of those candidates to be female is 0.3. This is our statement that says 3 out of 10 candidates are female. And notice that we make this claim under the empty context. We have, assumingly, no idea how that selection was generated. The program, we are philosophers and we have no idea what the program does. It's generated that. Okay. What we can do though is, for simplicity, let's assume that our shortlisting adds an additional criteria, say applicants must be Italian for some strange reason. Then what we want to compare this shortlisting with is the probability distribution of being female in the Italian population as of 2018. This might be they've changed it now. That probability, the probability of being a female in the Italian population is 52%. Happens to be that. Now, what we want to do is to check whether 52% is within the confidence rate, within the confidence in 95% confidence interval of the range centered around this value, 0.3. Now, it happens to be the case. So 3 out of 10 shortlisted candidates will be a trustworthy selection if that shortlisting is made with respect to a probability distribution that associates 52% to being a female in the population of interest. Notice that if we do this with a larger shortlisting set of candidates, shortlisted candidates, say 30, and we keep, say, the value 7, so we do not increase proportionally, but we keep it to 7, then this value is no longer, so the confidence interval centered around these 2 values makes this value outside of that confidence interval, right? So this selection is no longer trustworthy in terms of fairness with respect to the gender candidate. In fact, any we can tell you precisely, in fact, how much that is trustworthy, because any selection that would be lower than 10 and higher than 21 female candidates will be considered untrustworthy. There's a typo of here. This is again 730. All right. So I hope I have managed to give you the idea of how the trust rule work for this property. To conclude, I want to give you a very quick overview of the meta-theoretical result that we get and why. So what we do is we define a term transformation relation. This is a syntactic operation that happens on terms in the calculus, and we want to identify 2 properties through this transformation. The first is called output preservation. It tells us the following: if I am given a term which has an associated type, I want to identify the transformation that either preserve or increase the probability of that type. within some range limit, right? So in other words, I want to know if I'm starting from a given assumption, which rule I can apply so that the output that the type has is preserved with at least the same probability. And the second is safety, which is the final result. If I'm given a term, the transformation that I identify by output preservation will also tell me that if I apply those rules, I cannot get any other result than I should. So the formal results are the following. First, identify the transformation of interest. So this tells you that if I have a judgment of this form with this term, this type, and this frequency, and I apply some transformations that give me another term with another, possibly another output and a different frequency. If those transformations are generated by a higher number of premises in a sampling rule, an update rule, or an plus elimination, or a times introduction, all those rules in the limit will make the difference between the theoretical probability A and the frequency f prime 0. So what this theorem is telling you is that if you have a derivation and you apply these rules, your probability tends to approximate, your frequency tends to approximate the theoretical probability that you should have, that you are assigning in the distribution. So what that is useful for? Well, it tells me that if I have a certain judgment at some point in my derivation and I apply transformation that corresponds to certain rules, so I develop my derivation tree according to some given rules, specific rules, then I know that what I will get at will have a distance from the theoretical probability assigned to the corresponding variable, which is smaller than the one I started from. And this is good, right? So what I want is to get closer and closer and closer to my ideal probability. We transform this in terms of trust, which is the rule that allows us to make that comparison. And our final result is progress, which tells us exactly which terms are trustworthy and which are not. I'll read informally the result. It says that if you have at some point of your derivation a judgment of this form, which assigns a frequency f to output beta for n execution of t, then either there are term transformation which brings you to a term t prime that are performed according to the rule that we have identified, and t prime is trustworthy, or you know that this object is already untrustworthy. So in other words, you can now distinguish between processes that are tending to become trustworthy and processes that are diverging from trustworthiness. All right, the combination of these two results is called safety. By output preservation, we identify those term transformations or rules applications which allow to increase the probability of a given output. And then nothing but the allowed output can be produced. And by progress, we know whether a process is trustworthy by inspecting the derivation. There are a number of related work. The idea here of the present work and these other works that we are developing is roughly always the same. We are looking at the evaluation of trust for computational processes based on what is called in the literature post hoc model evaluation. In other words, we are always looking at the behavior of a given process and the model that is supposedly identified, transparently described, and then we define methods to compare the behavior of the current process or computational program with the model that we want to have, and we define criteria like trustworthiness, accuracy, by comparison of these two formal objects. Notice that the type of problems in other similar probabilistic proof system is never strictly the same. For example, we are looking at Markovian semantics and model checking with Alberto Termine's PhD here, and we have done work in that direction. Okay, I apologize if this was a little bit rushy towards the ends. There are a number of extensions that I will mention if you're interested. So thanks.